So in this module, module 3.2 for ME14 Mechanics of Solids course, we're going to continue on with some more example problems. So for this second section of module 3 here, what we're going to do is apply some of the governing equations and concepts and theories that we saw within module 2 in chapter 2 from last week. So let's take a look at example problem 2.21. Now in this problem here we have a truss. They tell us it's a steel truss, and they also give us our modulus of elasticity here. The E is equal to 29 times 10 to the 6 psi, and we can see the loading shown down below in our diagram here. We have this 50 kips loaded at point B going straight down there. Now from this information they want us to determine the deformations of members AB and AD. So let's take a look. AB goes from there to there, and AD goes from there to there. So we're just looking at this half of the truss system over here, and we can see this is symmetric. From B to D we have a distance of height here of 8 feet, and between A and D we have a distance of 13 feet, and between D and C we have a distance of 13 feet there. We can see the different types of connections and supports that we have at all these points here. So knowing their cross-sectional area, so they also tell us the cross-sectional area of AB being 4 inches, so that's right from here to here, A to B is 4 inches squared, and from AD down here, the cross-section of this member here is 2.8 inches squared. So that's all information they're giving us in the problem statement in the initial given diagram. We know what we're looking for here is the deformations, or deltas, of AB and AD. So from here, what we want to do is take this information from the given diagram and our problem statement and create our setup page. So that's what I do here. I create my setup page here. I say, okay, this is problem 2.21. I redraw a simplified version of my diagram over here with the pertinent information, and then I create my given section. Between the initial given diagram and the word problem, the problem statement, what do I know? Well, they give me my modulus of elasticity. We're dealing with steel, so this is 29 times 10 to the 6 psi. So again, I have my variable, I have my numerical value, the units that it's in, and how it relates back to my problem. Now I also have my length of AD right here, so here's LAD right there. This is 13 feet, I write that in. LAD is equal to 13 units of feet. Now I do a conversion. I see this is in inches here for PSI, so I convert this right here to inches as well, just in case. So this length is 156 inches. Now I do the same thing over here, LDC over here. This is the same length. This is at 13 feet. It's 156 inches. I may or may not need this, but right now for my givens right here, I'm going to write them all down. Even though I'm only dealing with the left-hand side of our triangle over here of our truss system, I'm still going to write everything down. So then I do LBD, so that's the length of this center member here, and that's given to us as 8 feet, or converting to inches, this is 96 inches. Now I know that the area of AB right here is given to me as 4 inches squared, and my area of AD is 2.8 inches squared right there. So I have all that information. I write that out. Everything is now in terms of inches. That's great. From there, now I go back to my problem statement, initial diagram, and ask myself, what am I solving for? What do they want me to find? Well, what they want me to find here is the deformations of members AB and AD. So again, AB being this member here, and AD being this member here. Well, the deformation, so what are those variable names right here? Well, delta AB and delta AD. So that, now I have everything in terms of their variable names. So when I go forward with my governing equations, I can plug directly in. So before I get in too far into my solution here, I want to take a look at some of the geometries. Now, there's certain information that I do already know that's given to me in the problem statement and initial diagram, but there's some other lengths and geometries that I don't know yet, and some dimensions that I'm going to need to calculate. So I can see here, I know that my length of AC is 13 feet. I know that my length of CD is 13 feet. And I know that my length of BC here is 8 feet. Well, I need to figure out what is my length of member AB for this problem here. At the same time, I'll do it for BD. They're both going to be the same. I can use Pythagorean's theorem here. A squared plus B squared is equal to C squared. The 13 squared plus my 8 squared is equal to my length over here, AB squared. So therefore, AB is equal to the square root of 8 squared plus 13 squared, or 15.26 feet. And the same thing, same triangle over here for length BD. So from that there, I can say, okay, my length of AD is 15.26 feet. I want to convert to inches, so the length of AD is equal to 183.72 inches, which is the same as BD over there. So they're both 183.72 inches. And this is my conversion I used right here to do that. So 15.26 feet, 12 inches in a foot. Feet cancel with feet when I do my unit analysis. There's where I get my 183.172 inches for the length of my member AB. So now from there, I may want to know what these angles are here. What is this? Is this of interest? Do I want to actually convert it to an angle, or do I want to leave it as it is there? So what I've chosen to do is, okay, go back to my trig here. Sine of this theta right here is opposite over my hypotenuse right there, where the opposite right here is 8. And my hypotenuse here is 15.26. So this is my sine of theta right there. So if I need to break things down in terms of components, I'm going to leave it there. I'm not going to convert it and simplify it down and back the angle out. I'm just going to say that the sine of theta is equal to that opposite over hypotenuse right there. So next I want to take a look at an overview of the free body diagram of the entire system right here. So this right here, this center member here is what we're going to call our zero force member, going from B to D right there. So what we have is that this 50 kips right here is going to be evenly distributed on these 2 points at A and C right there, making them both 25 kips apiece. This is just a quick overview from statics here, again with a zero force member in the middle right there for this style of truss. So this lets us know that FA is equal to FC is equal to 25 kips, just evenly distributing based on the geometry of that 50 kip load at the top there. So next thing we want to do is move on with our free body diagram here. So for this free body diagram, we're going to look at just joint A down here. If you remember, we're really concerned about AB and AD for the solution. We're looking for those deformations there. So the first thing I do is I draw my free body diagram at joint A, and I include my coordinate system that I want to go with. I'm saying that y is positive up and x is positive going to the right. So now I draw that out over here. What are my forces acting? Well, we've got this reactionary force down here at A of that 25 kip. And then we have right here coming off, we have this force from member AD, and we have this force from member AB. So these are our three loads being applied for our free body diagram at joint A right there. So what I want to do is let's break this down into x and y components and deal with each of these separately. So the first direction I'm going to look at is just my y direction here. And again, I recall my y is positive going up. So what is the summation of forces? What forcings are acting in my y direction, or a component of that force acting in the y direction at my joint A? Well, I can see here purely in my positive y direction, I have this reactionary force right here of 25 kips. So I put that in right there. And then I have this FAB. Now I've already done out the trig here. I could have figured out the angle if I wanted to, but I just left it in terms of the opposite and hypotenuse right here for the sine of theta right there. So this is where I get this 8 over 15.26 to break this down to get my y component here of my FAB force right there. And I can see that FAD only acts purely in the x direction. There is no component in the y direction, so that's not included here. So I look at this, equilibrium equal to 0, so my only unknown is my FAB. I can rearrange now and solve for this FAB, and when I do that there, I have 8 over 15.26 times my FAB is equal to a negative 25 right there, or my FAB, when I plug that in, is equal to negative 47.701 in units of kips. So from there, I want to move on, do the same thing, free body diagram, joint A, but now I want to look in my x direction here. So if I go back up to my free body diagram, paying attention to my coordinate system here, and I say in my x direction, well, this doesn't act in my x direction, but this and a component of FAB both act in my x direction. So now rather than doing the y component of FAB, I do my x component. So now I have 13 over 15.263 right there, times my FAB to get my x component, and that's going to be acting in the positive x direction to the right. And my FAD is also acting in my positive direction to the right there, purely in the x direction. So now I have this relationship for the summation of forces in the x direction for equilibrium. So two unknowns technically in this right here now, but I already know the FAB I'd solved for from my y direction previously, and that is negative 47.701. So I can take that and plug that in for my FAB right there, multiply it again to get the y component of that now, plug in everything I know, so FAD is plus my breaking this down into components, my 13 over my 15.26 times that FAB of negative 47.701 that we've already found is equal to 0, only unknown is FAD. I can solve for that. My FAD is positive, as it should be. It's acting in the pure x direction here, 40.625 kips. So now is a good time to go back up to our setup page and figure out what exactly we are solving for in this. That's great that we found those forces, but what we really wanted was these deformations right here, and we want it in both AB and in AD. So let's take a look at AB first, and we say, okay, what is our general equation? If we're looking for deformation, what is our general equation? So we can reference back to equation 2.9 on page 70 of our textbook. And a little side note I want to mention here, 1 kip is equal to 1,000 pounds. If we're dealing with pounds here, we want to do that conversion. We'll show that in some unit analysis later. And we look at all these variables. We have our delta, we have our load, we have our length, we have our area, and we have our modular elasticity here. So I'm going to take that information from what we've calculated so far, and what we're given in the problem statement, which is back on our setup page, and write it all here. So I have my FAB of negative 47.701 kips, my FAD here of 40.625 kips, my length of member AB of 183.172 inches, my length of AD of 156 inches, my area of AB of 4 inches squared, and my area of AD of 2.8 inches squared here, and my modular elasticity for this material of 29 times 10 to the 6 in units of PSI. So now what I can do is let's arrange equation 2.9 specifically for our problem here for member AB. So delta AB, or deformation of this member here, is equal to the force acting on AB times the length of AB, all divided by our modular elasticity times our area, cross-sectional area of AB there. So now we can use all that information that we show up here and plug in for our known values. So our delta AB is, when we say our F of AB, well, that's negative 47.701 from up here, and our length of AB is 183.72, so I put that in right there, and I see my E, my modular elasticity, is 29 times 10 to the 6 psi. I put that in there, and my area of AB is 4 inches squared. I put that in there. Now off to the side over here, I put out my units, because I want to do unit analysis and make sure I get my deformation in units that make sense. So this right here, I convert now. You can see 10 to the third there. I've converted it to pounds from kips right there. And this is in inches right here for my length. Then I have this in PSI, or pounds per square inch right there, and this is in inches squared, so I can see inches squared cancels with inches squared, pounds cancel with pounds. I'm just left with inches for units. Does a deformation in inches make sense? Yes, it does. Plug this all in, solve this. My delta AB is equal to negative 0.0753 inches. So that is my deformation of AB, which is the first portion of the first part of the problem they asked us to solve for. So from there, we need to do the second portion here, which is to take a look and find the deformation in member AD. So I again retake that equation 2.9 from our textbook there and say our delta AD is equal to our F on that member there, AD, times the length of AD divided by our modular elasticity times that cross-sectional area of AD as well. Write out all of my knowns over here again, so I have all those variables I can plug right in. So I say my delta AD is now equal to, my FAD is this 40.625 kips, so times 10 to the positive third in pounds, 156 in units of inches right there, 29 times 10 to the 6 in pounds per inches squared in PSI, and 2.8 in inches squared right there. Again, the units cancel out, we're left with just inches, and it's positive deformation in this case here of delta AD is equal to 0.078 in units of inches. Next, we're going to take a look at an example problem involving two cylindrical rods. So here in problem 2.39, we see we have two different rods here. We have rod AC, which is made of aluminum, and rod CD, which is made of steel. So up to this point, we've really seen only a uniform material throughout this. So now we're going to introduce two different materials right here. So these two different rods of steel and aluminum are going to be joined together at point C down here, are restrained by rigid supports at A and D. So it's rigidly connected over here at A and at D right there. Now, for the loading shown here, that we have our two different modular elasticities right here. We have our 10.4 times 10 to the 6 psi for our aluminum, and we have our 29 times 10 to the 6 psi for our steel. So you can see the indices, S for steel, A for aluminum right there. Now, what are they asking us to solve for in this problem here? Well, they want us to determine two different things. First, in part A, they want us to find the reactions A and D, and again, we recall that this right here is rigid supports at A and D right there. And then part B, they want us to find the deflection of point C where the two rods join together, where the aluminum rod and the steel rod join together. Now down here in our diagram, we're also given some more information that's not in the problem statement. We have our length from A to this point B, and we can see at point B there's a load, an internal load here of 18 kips right there, going over to the positive to the right. Then from B to C, we have this distance of 10 inches, and then from C to D, we have a distance of 10 inches as well. And we can see at point C here, there's another load of 14 kips going over positive to the right. We can see that our steel rod CD has a diameter given to us as 1 5/8 of an inch diameter, and for our AC, it's a smaller diameter rod of 1 1/8 inch right there. So we have a lot of information again given to us within the problem statement and this initial given diagram. From here, we want to go ahead and create our setup page. So here we have our setup page now. I've labeled my problem 2.39 right here. This is two cylindrical rods, one being steel, one being aluminum right there. I redraw out my simplified version of my diagram right here with all my pertinent information. And over here on the left, I write out all my givens. And you can see I have quite a few givens right here. Well, I know that my rod AC is aluminum. I'm going to make that note. I know that my rod CD is steel. I make that note over here in my givens as well. I know my modular elasticity for my aluminum rod section, which is AC, is 10.4 times 10 to the 6 psi. My modular elasticity for my steel is 29 times 10 to the 6 psi, and that is for CD right there. My diameter of AC is 1 1/8 inch. My diameter of CD is 1 5/8 inches. Now my length from A to B is 8 inches. From B to C is 10 inches, and my length of C to D is 10 inches there. So even though it's in our diagram right here, having it out with our variable name with the correct indices is going to help us when we start plugging into our equation to solve for what they ask us to solve for, which is, in this case here, what they want us to find is two different things, part A and part B. In part A, they want us to find the reactions at A and D. So what are those variable names? Well, that's RA and RD is what I'm going to call that, my reaction at A and my reaction at D. And I also need to find my deflection at point C, so my delta C. So now I have everything nice and organized here, all of my given information, my initial diagram, and what they're asking me to solve for. This is going to be great as I move forward. I can come back here for all this information to plug into my governing equations. So now with that information there, and after reading through the problem statement, looking at the diagrams, I can begin my solution here. So first thing we want to do is break this down into individual parts. So there's two different rods, and each one has a different material, and then there's different loading points of the rods, different reaction forces, so a lot of different components and parts within this problem here. Let's just look at just the aluminum rod. So we're just going to look at rod AC right here. Well, what is the area of this rod? We're given our diameter. So from diameter, we have this relationship for area right here. And notice I have my indices here just to denote which portion of the project or part I'm dealing with here. So I'm dealing with my aluminum rod, rod AC. So the area of AC is equal to pi times my diameter of AC over 4. My diameter of AC, I can go back to my setup page and look that up, and that is 1.125 or 1 1/8 inches. I plug that over here for my diameter of AC of 1.125. Multiply this by pi over 4 when we square it, and we end up with, when we do that out there, AAC is equal to 0.99402 in units of inches squared. So going on from there, we're going to do the same thing, but now for our steel rod, which is rod CD. So my area of CD, still in general form here, is pi over 4 times my diameter of CD squared, where my diameter of CD is 1 5/8 inches or 1.625 inches. I can take that value, plug it in here for that diameter of that rod there, so I can say the area of CD is equal to pi over 4 times 1.625 squared. I do that out here now, and my area of rod CD, my steel rod, is 2.0739 inches squared. So the same method I did for my aluminum rod, do the same thing for my steel rod here. The only difference now for area calculation is it is a larger diameter when I plug in for area. So with that information there, now we can actually begin getting into our solution right here. So I want to break this down again. So the first thing I do is I draw out my diagram here for the entire system right here, A, C, D, that whole rod, where A to C is going to be of aluminum and C to D is going to be of steel right there. But I can see there's also this point B where I have this 18 kip load applied right there. So I'm just going to look at this part right here, portion A to B, which is all aluminum at that point right there. And I want to calculate my delta AB, my deflection in AB right there. So I go back to this equation 2.9 as my governing equation here in general form. We have this as our load P times the length, in this case here it's the length of AB right there, divided by the modulus of elasticity for aluminum, times our area of AB right there. Well, we've just calculated our area of AB. We have all this other information here, so I can reference back to what I've solved for and what's on my setup page there. And I like to rewrite it all right here, so I have it in front of me as I plug in. Well, my load here, I can see from my diagram right here, is simply just going to be this RA acting at A right there. So that's my load right there. I have my length of AB. If I go back to my initial setup page, that's given to me as 8 inches. My modulus elasticity is 10.4 times 10 to the 6 in units of PSI, and I just calculated my area of AB to be 0.99402 inches because that's for the whole rod AC. So AB is the same diameter, same cross-sectional area all the way across that there. So I can take this information, plug it back into this general governing equation here. I see that my delta of AB is equal to, now on the top right here for my load, I have my RA, that reactionary force to A that I'm going to be looking for. I have that length of AB, which is 8 inches. I have my modulus elasticity, which is 10.4 times 10 to the 6 psi for aluminum. And I have my area of AB, which I've just calculated to be 0.99402. Plug these all in, solve them out, do my unit analysis, double check. I end up with delta AB is equal to 0.77386 times 10 to the negative 6 times my RA. So two unknowns in this equation. We're going to continue on from here and look at the next section within the aluminum rod. So that's what we do there now. Now we already looked at AB, so next we're going to look at B to C right here. Again, for the aluminum rod, I still have equation 2.9 as my general equation. We apply it for this specific portion here. So I have my load P times my length now of BC in this instance here, divided by my modulus elasticity, still for aluminum, times the area of BC, which still would be the same area, cross-sectional area, as we had for AB there, because the diameter is the same. But I still come down here, I write out all of this information, my variable name, my units and my numeric value for this here, plug those all in. So my P in this case here, if I look at B to C right here, I'm going to have this RA minus this 18. So RA is going in this direction here. My 18 is going in the opposite direction here, so the sign convention is different. So my load here is going to be RA minus 18 times 10 to the third. My length of this here is given in the problem statement. I can go back to my initial setup page here. This is 10 inches. My modulus elasticity for aluminum, 10.4 times 10 to the 6 psi. And my area here for this member BC is 0.9942 inches squared, the same as it was for AB because the diameter is the same. Plug those all in. I can see my delta BC down here is equal to that load of RA minus the 18 times 10 to the third times that length of 10 times the modulus, or divided by my modulus elasticity times that area of BC there. I plug this all in. I end up with my delta BC, my deflection in BC is equal to 0.96732 times 10 to the negative 6 times that same RA minus 117.412 times 10 to the negative third. So again, I still have two unknowns in one equation right here. So now, as you can imagine, we're going to move on to the next member here, CD. So now we continue on to that last section over here, CD. So this now is steel that we're dealing with here. So my delta CD is equal to this relationship here where I have my load times the length of CD divided by my modulus elasticity for steel now times the area right there based on my diameter of CD there. I still write everything out over here. So for this particular problem, my load is equal to my RA right here, positive direction, minus this right here is 18 times 10 to the third right there, going the opposite direction there, so the negative sign, minus 14 times 10 to the third. There's my 14 kips right there, acting at point C. And my length of this CD member right here is 10 inches. My modulus elasticity for steel, given to me is 29 times 10 to the 6 psi. And my area for CD is equal to, based off my diameter for that section of the rod, 2.0739 inches squared. Plug all this back in now to this equation here. We end up with my delta for this member CD rod, the steel portion of the rod right here, is equal to my RA minus 32 times 10 to the third, which is combining those two terms there, times 10 inches divided by my modulus elasticity for steel, times right here my area of CD from above there. I plug that right in. So I do this out here. My delta CD is equal to, in this case here, 0.16627 times 10 to the negative 9th times RA minus 5.3206 times 10 to the negative 3rd there. So I now have this relationship for the last section of the rod, the steel section there, delta CD. And this we can see there's two unknowns in one equation there as well. So where do we go now? We have these three different equations, but each of those equations has two unknowns. So essentially we have four unknowns because RA is the same in all of them and only three equations. So we need a third relationship, a third equation, so that we have the number of equations match our number of unknowns, four equations, four unknowns. Well, what we can do here is we have this relationship here for the deflection of the entire rod. So we can say the deflection of AD is equal to the sum of the deflection of AB, the deflection of BC, and the deflection of CD right there. But we know that since D cannot move relative to A, that total deflection right there at the fixed support right there is 0. So we can plug in for all of those right there for our delta AD being equal to AB, BC, and CD, and we end up with this relationship right here where we have now, when we plug that in there, 1.90475 times 10 to the negative 6 RA minus 22.733 times 10 to the negative 3rd. When we add all these guys together, and that's equal to AD, which is equal to 0. So we can set that equal to 0 there. Therefore, now we only have one unknown. Our only unknown is our RA. So we can rearrange this a little bit right here, and we can say, okay, let's set this equal to 0 first. Then we can move our negative 22 over to the other side here. Then we can divide through by our 1.90475 times 10 to the 6, leaving RA alone by itself. Do our math here, and our RA is equal to 11.9349 times 10 to the 3rd pounds. So that's one of the things it asks us to solve for, was our reactionary force here at the support at A. So our RA is equal to this value here now. So now in order to find our reaction at D, we can say that our reaction at D is equal to the internal forces right there minus our RA. Well, we know our RA now that we just solved for. We can plug that in there. Combine these two together. Our RD is equal to 32 times 10 to the 3rd. Minus that RA function, or RA value there that we can plug right in. So RD is equal to 32 times 10 to the 3rd minus 11.9349 times 10 to the 3rd. So RD right here, when we do our equilibrium balance out right here, RD is equal to 20.065 times 10 to the 3rd pounds. So that gives us our RD and our RA, which is what they'd asked us to solve for in the problem. Now, we can move on to part B for the problem here. So at part B, they asked us to find our deflection at point C. So we come up with our general equation. We go back to that 2.9 in our textbook here. Apply it for this specific problem here, where our load right here is going to be this RD that we just solved for in part A, times our length of that member CD, divided by our modulus elasticity right here for steel, because we're dealing with just that steel section right there, times our area right here of CD based upon the diameter of the steel section of the rod CD there. We can plug in our known values right here. We write them all down. Our RD, we just solved for, to be 20.065 times 10 to the 3rd pounds. Our length of this member is 10 inches. Our modulus elasticity for steel for this section here is 29 times 10 to the 6 psi. And our area for this member CD is equal to 2.0739 inches squared. So I can take all that information, plug back into our governing equation 2.9 right here. And when we do that, we end up with our delta C, our deflection at C right here, is equal to that 20.065 times 10 to the 3rd times 10 inches divided by our modulus elasticity, 29 times 10 to the 6, times right here our area of CD, our 2.0739. Plug that all in. What we find is our delta, our deflection at C, is equal to 3.34 times 10 to the negative 3rd inches. Inches is the units we want to be in. We can do it our unit analysis to double check that. And that answers our final part, part B, for this problem here. So now we've completed all the things that they'd asked us to solve for.